Have you ever heard of the concept of wave-particle duality? It's one of the weirdest, but most fundamental ideas in modern physics. It says that tiny things like electrons can act like both a solid particle and a spread-out wave. Sounds mind-bending, right? Well, a huge piece of this puzzle was solved by a man named George Paget Thomson, and his story is fascinating because his own father, J.J. Thomson, had won a Nobel Prize for proving the electron was a particle. Talk about a family debate. Today, we're diving into the life and work of G.P. Thomson, the man who showed the world the electron's wavy side. George Paget Thomson, or G.P., as he was often called, was born in 1892 in Cambridge, England. You could say physics was in his blood. His father, Sir J.J. Thomson, was the legendary physicist who discovered the electron in 1897. Imagine growing up with a Nobel laureate as your dad. J.J. famously described the electron as a tiny, definite particle, like a minuscule billiard ball. This became the standard view for decades. G.P. followed in his father's footsteps, studying mathematics and physics at Trinity College, Cambridge, the same place his father was a master. He was clearly a brilliant student, but his academic career was soon interrupted. When World War I broke out in 1914, Thomson joined the army. He served in France, but was soon called back to England for more technical work. He spent time working on aerodynamics at the Royal Aircraft Establishment at Farnborough. This experience with practical, hands-on engineering and experimentation would prove invaluable later in his physics career. It taught him how to build and design sophisticated equipment, a skill that would be crucial for the discovery that would make him famous. After the war, he returned to Cambridge and then became a professor at the University of Aberdeen in Scotland in 1922. It was in Aberdeen that the magic started to happen. In the early 1920s, the world of physics was buzzing with radical new ideas. A French physicist named Louis de Broglie had proposed a wild hypothesis. If light waves could sometimes act like particles, which Einstein had shown, then maybe particles, like electrons, could sometimes act like waves. De Broglie even came up with an equation to predict the wavelength of a particle. At first, many scientists were skeptical. An electron as a wave? It seemed absurd. How could a solid little speck also be a smeared-out wave? This is where G.P. Thomson enters the picture. He was intrigued by de Broglie's idea and decided to test it. He thought, if electrons really are waves, they should behave like them. And what do waves do? They diffract. Think about ocean waves hitting a harbor wall with a small gap. As the waves pass through, they spread out in a circular pattern. This is diffraction. The same thing happens with light waves. If you shine a light through a very narrow slit, it will create a diffraction pattern of bright and dark bands. Thomson realized he could do a similar experiment with electrons. He just needed a slit that was small enough, roughly the same size as the electron's predicted wavelength. Where could he find such a tiny structure? He cleverly realized that the atoms in a crystal are arranged in a regular repeating lattice. The spaces between these atoms could act as the perfect set of slits for electron waves. So, he set up his experiment. He built a device similar to a cathode ray tube, which shoots a beam of high-energy electrons. He placed a very thin film of metal, like gold or celluloid, in the path of the electron beam. The electrons would pass through the crystal structure of the metal foil. On the other side, he placed a photographic plate to detect where the electrons landed. If electrons were just tiny particles, like his father had said, they should have just shot straight through the foil and created a single small dot on the photographic plate, maybe a little scattered, but mostly a central blob. But that's not what Thomson found. When he developed the photographic plate, he saw a stunning pattern of concentric rings. It was a beautiful, clear diffraction pattern. This pattern could only be created if the electrons were behaving as waves, diffracting as they passed through the crystal lattice and interfering with each other. The bright rings were where the electron waves added up, and the dark spaces were where they canceled out. It was undeniable proof that electrons, these supposed solid particles, had a wave-like nature. What makes this story even more incredible is the timing. Unbeknownst to Thomson, two American physicists, Clinton Davison and Lester Germer, were conducting a similar experiment at Bell Labs in the United States. They were firing electrons at a nickel crystal, and after an accidental lab mishap that changed their crystal structure, they also observed electron diffraction. Both Thomson and the Davison-Germer team published their results in 1927, independently confirming de Broglie's hypothesis from different angles. It's a classic example of simultaneous discovery in science, showing that the time was ripe for this revolutionary idea. For their groundbreaking work, G.P. Thomson and Clinton Davison shared the Nobel Prize in Physics in 1937. And now for the beautifully ironic part of the story. J.J. Thomson won his Nobel Prize in 1906 for proving the electron is a particle. 31 years later, his son, G.P. Thomson, won a Nobel Prize for proving the electron is a wave. It's often joked that the father won the Nobel for showing the electron was a particle, and the son won it for showing it wasn't. But that's not quite right. The reality is much more profound. They were both right. This is the core of wave-particle duality. An electron isn't just a particle, and it isn't just a wave. It's something that has properties of both. Which property you observe depends on how you measure it. If you set up an experiment to find its position, like J.J. Thomson did, it behaves like a particle. If you set up an experiment to see how it travels through a crystal, like G.P. Thomson did, it behaves like a wave. It's one of the foundational principles of quantum mechanics, and it highlights how strange and counterintuitive the subatomic world truly is. Thomson's discovery had immediate and lasting impacts. The technique he pioneered, called electron diffraction, became a powerful tool for scientists. By analyzing the diffraction patterns created when electrons pass through a material, researchers can determine the precise arrangement of atoms within it. This has been vital in material science, chemistry, and biology for studying the structure of everything from new metal alloys to complex biological molecules. After his Nobel-winning work, Thomson's career continued to flourish. He moved to Imperial College London and later became heavily involved in the early stages of nuclear physics research in Britain. During World War II, he chaired the crucial MAUD committee, which determined that an atomic bomb was feasible. After the war, he returned to academia, becoming Master of Corpus Christi College, Cambridge, and continued to advocate for the peaceful use of nuclear energy. He was a scientist who not only made a fundamental discovery about the nature of reality, but also engaged with the profound technological and ethical implications of science in the modern world. So, the next time you think about quantum physics, remember the amazing story of the Thomsons, a father and son who, together, gave us a complete picture of the electron. J.J. showed us its particle face, and G.P. revealed its hidden wave nature. G.P. Thomson's elegant experiment didn't just win him a Nobel Prize. It fundamentally changed our understanding of matter and opened a door to a quantum world that we are still exploring today. His legacy is not just a pattern of rings on a photographic plate, but a profound shift in how we see the very fabric of the universe. Thanks for watching. If you found this journey into the quantum world fascinating, don't forget to hit that like button and subscribe for more stories from the history of science. Let us know in the comments what other scientific pioneers you'd like to learn about. See you next time.